Okay, now we're going to introduce the concept of work. So, yes, now you're going to need to do some work. Before we do that, we're going to first remind ourselves that we've talked about forces in Newton's laws of motion. But forces were related to instantaneous rates of change, otherwise known as accelerations. So, a force gives an acceleration. That's the rate at which something is changing at a particular instant in time. Now, what we want to consider is what is the overall or cumulative effect of these small instantaneous changes as they occur over time. There's two ways to calculate this. First, we can consider applying a force as an object moves through space and say what is the product of force times the displacement the object makes. Second way we can do is take and multiply simply the force times the amount of time that the force was applied. These are two new concepts we're going to introduce. The first one we're going to call work, and that's the topic of this chapter. Then after that, we're going to look at impulse, which is our next major topic. Now, when we're talking about the first one, we're multiplying a force, which is a vector, times a displacement, which is a vector, and there's two ways to multiply vectors together. For our purposes, we're going to define work to be the dot product of these two vectors. So, our definition for work will simply be the dot product between force and the displacement. Note here we're going to initially consider a simple case where the force is constant in both magnitude and direction. So the work will simply be the magnitude of the force times the magnitude of the displacement times the cosine of the angle in between them. And because we're using a dot product, that means work will be a scalar quantity. So if we have this force right here acting on this box as it moves across the floor and making a displacement of delta x, and the force is at an angle theta with respect to the horizontal, the work done will be shown by this vector diagram. We have the force and the displacement and the angle in between them, and the dot product will be f delta x times the cosine of this angle theta. Now we're introducing a new quantity. Whenever we do that, we need to determine is that quantity a scalar or a vector. Because we're defining it as a dot product, that makes it to be a scalar. We also need to define units. Well, the units will be units of force, which are newtons, times units of displacement, which are meters. That would make it a newton meter. Well, that's just an awkward term to be using. So it is named after one of the people who worked on energy, namely James Joule. He's one of many people that worked on it, but he's the one who gets credit for it. So the unit for work is named after him, and it is called the joule. A joule is therefore the amount of work done when a force of 1 Newton is applied over a displacement of 1 meter. So a joule is a Newton meter. Now, let's consider what this means. First, we always have to remind ourselves that work is always something that is done by a particular force on a particular object. It is one way of describing an interaction, where the force is applied on an object and the work is done by that force on an object. So let's consider an example. We've got Alice here who is lifting a box from the floor and putting it up on a table. Alice is applying a force, so Alice is doing work on the box. But gravity is also applying a force, so gravity also does work on the box. In this particular case, those are the only two forces we will consider. Therefore, the net work is the sum of the work done by all of the forces, which is the work done by Alice plus the work done by gravity. So we can distinguish between work done by a particular force, in this case Alice, and the total work done by all of the forces. And it's important sometimes to make sure we have that distinction in mind. Another thing is just to remind ourselves of one of the ways we can interpret dot products. Namely, I can take the cosine function and apply it to just the force vector, and then I get the component of the force which is parallel to the second vector, of the displacement vector, and see that the only thing that contributes to the work done is the force that is parallel to the displacement. The component of the force that is perpendicular will not do work. It will only change the direction of motion. And since work is a scalar, the direction of motion is irrelevant. So the only part of a force that does any work is the component that is parallel to the motion, not the part that is perpendicular. Now we'll introduce this now, but this is our next major topic, is that work does something, it changes something. And what it changes, we're going to call the energy. So work will equal the change in energy of an object. This is just a preview. We will derive exactly what that means later. But for the time being, we will say work changes something about the object, and that something we're going to call energy. Now we can remind ourselves that dot products can be positive, negative, or zero. So what does that mean? If the work is positive, so the dot product is positive, that means the force and the displacement are sort of in the same direction, or the angle between them is less than 90 degrees. That means the change in energy must be positive, or we're adding energy to the object. If the force and the displacement are sort of in opposite directions, so the dot product is negative and the angle in between them is greater than 90 degrees, that means the change in energy is negative, or we are removing energy from the object. If the dot product is zero, that means no change in energy is happening. Any change would simply be a change in direction, or the object turns, but work is a scalar, and that means energy is a scalar. That means there's no change in energy. The object is merely changing its direction, and that doesn't affect the scalar quantity. Now let's consider a couple of examples. First, we'll take an object going around in a circle. This green ball is going around in this circle. For it to do that, there must be a centripetal force which acts towards the center of the circle. That centripetal force could be the tension on a string. It could be a frictional force between the object and the surface. It could be gravity. We're not going to worry about the nature of the force, but there has to be a force acting somewhere towards the center of the circle. The motion is tangent to the circle, so this blue vector right here represents the velocity, and the displacement is always parallel to the velocity. So if the object is moving in that direction, the displacement is in this direction. That means the force is radial, the displacement is tangential, and the angle between a radius and a tangent is always 90 degrees. So that means the centripetal force is perpendicular to the motion. It only changes the motion, direction of motion. It does not change the energy. The velocity stays constant in magnitude. This means the centripetal force does no work because it is perpendicular to the motion, and the dot product is zero. Centripetal forces do not do work. Now, in our original definition of work, we considered a constant force. Well, how would we define work if the force varies? Particularly if it varies with position as an object moves. We have an object moving along the x-axis, and it's the force acting on it could be changing. Well, here what we're going to do is define the work as the integral of the dot product between the force and a small displacement, saying that over an infinitesimally small displacement, the force will be approximately constant. The work, therefore, will be F times dx. What we're going to do is add up all of these small contributions as the object moves from x1 to x2 over a distance delta x. That means the work will be the area under this curve, where this curve is the function of the force. So the force will vary here from 200 newtons to a bit over 300, and then back down close to zero. This right here will be this area will be the total work done by this force as the object moves from x equals 0 to x equals 4. So the work done will be the area under this curve.